All right, let's go ahead and talk about precipitation reactions. And so a precipitation reaction is essentially when you have two aqueous solutions. So you have two compounds that are dissolved in solution and they're in separate solutions, and you mix them together. A chemical reaction occurs where one of the products is no longer aqueous but solid. So again, you have two aqueous solutions, mix them together, and a solid is formed. Now, the reason why the solid is formed is because the product that is produced is insoluble, which means it cannot dissolve in water. What then ends up happening is a solid is formed. Now, there are some situations where you can have a liquid form that's not dissolved in water, but we'll talk about that later. But the insoluble compound that settles out of solution is called a precipitate, and that is going to be a solid. Sometimes you'll see it's a certain color, it looks kind of cloudy, but after a while it kind of settles out of solution and sinks to the bottom. Now, when we are looking at chemical reactions and we're trying to determine if something is soluble or not, what we need to do is look at our solubility rules, and our solubility rules will tell us, the solubility will tell us what is soluble and what is insoluble. In other words, what is able to dissolve and what's not able to dissolve in water. This here is your solubility rules for ionic compounds. And so if you take a look at the top half of it, on the left shows the ions that are soluble in water. What that means is that if a compound has one of those ions, it is going to dissolve in water. It is soluble. It will be aqueous. The bottom half shows ions that are insoluble. They're the ions that when you put them in water, they will not dissolve but will remain a solid. So if there's a compound with one of those ions, it will form a solid. Now, if you take a look on the right column shows the exceptions to that. So if you take a look, lithium ion, that is a soluble ion, and with the exceptions, there is no exception. But go ahead and go down to the third row, where you see the chloride ion, the bromide ion, and iodide ion. Notice how chloride, bromide, and iodide, those are soluble in water. That means that they will dissolve. But there are exceptions. For example, silver, mercury, and lead, when those compounds are with one of those ions, it will not dissolve. So for example, again, chloride ion is soluble, but silver chloride is not, because silver is one of the exceptions. Look at the bottom, it's the same thing but opposite. The bottom shows you what's insoluble. Carbonate, which is CO3 is insoluble. It will not dissolve in water, so it'll be a solid, except if it's lithium. So if we had lithium carbonate can dissolve in water because lithium is one of the exceptions. Sodium's an exception as well. And so that's kind of how you look at this chart. Now we'll do practice problems where we determine, what is soluble or not. Now, something that we want to talk about is something called a net ionic equation. And a net ionic equation includes only those ions which undergo a change in their state, really. And so, in other words, a net ionic equation shows those ions that start off as aqueous before the chemical reaction, and then they're solid after the chemical reaction. So before the chemical reaction, they're aqueous, but then they're solid after the chemical reaction. And again, we're going to look at a practice problem of this to really understand it. Now, ions that do not take part in the chemical reaction and are found to be aqueous before and after the chemical reaction are called spectator ions. Now, those ions, again, they start off as aqueous, and when they're aqueous, just remember that when they're aqueous, they're not together. So if we have an aqueous compound, it is dissociated in solution. Again, look at the top, the dissociation part. We talked about this in a previous video, but those ions are separate from each other. They're floating around in solution. And spectator ions are ions which are aqueous before, they're just floating around in solution before, and they're aqueous after. They're just floating around in solution after. So they really don't take part in any change because they're aqueous before and after. Again, we'll look at examples of this as we go. And that's all there's for the notes. We're going to go ahead and get into that bottom part of your notes here. And here we go. All right, so when we are wanting to write the net ionic equation, what we want to do is we want to look at what starts off as an aqueous ion and what but doesn't end up as an aqueous ion. So it starts off as an aqueous ion, but then in the product side, it's no longer an aqueous ion. And so what we're going to do is I'm going to show you sort of the long way of doing this, and then I'm going to show you how you can quickly identify the net ionic equation by looking at the chemical formula here, the chemical equation. So let's go ahead and start doing that. So the first thing we're going to do is we're going to take each compound here, and we're going to break it up into its ions, right? And so again, just a quick reminder, this, for example, when you have something like this, and it's aqueous, what that means is that in the solution, these are not together. They are separate. There's a 2 there. They're separate. So they're not together, they're separate ions. And they're just sort of dissociated, floating around in solution. Now, what's different is this right here is not aqueous, it's solid, which means that they do not break apart. So this here, it does not do this. It does not do this. Instead, it remains together intact. And so that's what we want to think about. So the ones that are aqueous, they do break apart, and the ones that are not aqueous, the ones that are solid, do not break apart, or the ones that are liquid do not break apart. And so notice this is aqueous, and this is aqueous. And so those are going to break apart when they are dissociated in solution. And so we end up with something like this. So the first thing we want to do is write it dissociated. First thing we do is we break apart the ions to show that they are dissociated in solution. And so this right here comes from that. Then what we're going to do is we're going to write this one right here. So we have the cadmium, which is a 2+, plus the nitrate, which is a 1-, but notice how there's 2 of them here, so we're going to put a 2. And then this is aqueous, and we're going to show those dissociated in the solution. And notice how there's a 2 here, so that 2 applies to all of them, so we're going to have 2 ammoniums plus 2 nitrates. Now notice this here, this one is a solid, so it is not dissociated in solution, but rather it stays intact and is actually probably settled to the bottom of the solution. So this is a solid. And so what we want to do is we want to look at what starts off as an aqueous ion but then is no longer an aqueous ion. And the way you can figure that out is by crossing out everything that you see on both sides that's an aqueous ion. Notice how this here and this here, they're the same thing. It starts off as an aqueous ion and it ends as an aqueous ion. And so this we can actually cross out. Then notice how this is also an aqueous ion here and here. It's an aqueous ion on both sides. So this also we cross out. But notice this here is an aqueous ion, but it's no longer an aqueous ion over there. It's a solid. And so we do not cross those out. And then this one, again, is an aqueous ion, but then it's no longer an aqueous ion, so we do not cross it out. And this is actually what we end up with. The net ionic equation is going to be this plus this yields this. And these are technically aqueous, so we can write AQ. And this here is the net ionic equation. Now notice what the net ionic equation is. So this is sort of the long way where you sit there and you break apart. Everything that's aqueous. So you show the ions dissociated. If it's not aqueous, you do not break it apart, kind of like that. Now notice whatever is solid, whatever is going to be solid is actually going to tell you what the net ionic equation is, because notice how the net ionic equation is the solid starting off as its aqueous ions and then coming together to make the solid. Now we need to talk about what spectator ions are. Spectator ions are those ions in which they do not change. So they start off as an aqueous ion and they end as an aqueous ion. And those spectator ions are going to be the things that we crossed out. Those are going to be the things that we crossed out. And so notice how the solid in the product side, so whatever is the solid product, contains those ions which are part of the net ionic equation. The aqueous product contains the spectator ions. So again, the aqueous product contains the spectator ions, and the solid product contains the ions that are part of the net ionic equation. So really it contains the net ionic equation. So let's go ahead and do some practice problems. Now if you take a look, here is, we're going to go through these. The first thing you need to do is you need to write out the formulas. Mercury, notice how mercury 2, that means that this has a 2 plus. If you look at the periodic table, you'll see chlorine here. Chlorine makes a 1 negative charge. And just a quick reminder, this is a 1 negative. These make a 2 negative charge, 3 negative. This is 3 positive. This is 2 positive and 1 positive. And so those are the charges. So everything in this column makes a 2 positive. Everything in this column makes a 1 positive. And then all of these here, just a quick reminder, all of these require Roman numerals. So they all require Roman numerals because they make multiple charges. And so when you see something like this, which is mercury 2, that means that the mercury is making a 2 positive. And then again, if you look here, the chlorine is making a 1 negative. Now potassium is right here, makes a 1 positive. Sulfide is right here, makes a 2 negative. And so I just like to go through, just like to write the charges above. And again, when we're balancing charges, we want to make it to where the charges balance. If we have a total of 2 positive, we need a total of 2 negative. The way we do that is with a 1:2 ratio. And we end up with mercury chloride with 2 chloride. So that is mercury 2 chloride. You need 2 chlorines to balance with the 1 mercury. This is aqueous, and we know that because look, it tells us right there. Plus potassium sulfide. Potassium is a 1 positive, this is a 2 negative, so we need 2 potassiums for every 1 sulfide. Again, this is aqueous because it tells us it's aqueous. Now this is a double replacement reaction, and what you do is you take the first ones, the metals, you take the metals and you make the metals trade places. You take the ion in the front and you make them trade places. And when you do that, notice how the potassium will end up with the chlorine and the mercury will end up with the sulfide. And so let's go ahead and do that. So the potassium ends up with the chlorine. But again, when those come together, you have to look at their charges. So the potassium does make a 1 positive, chloride makes a 1 negative, and that's a 1:1 ratio. So that works out. Plus the mercury and the sulfur come together. Again, you have to look at the charges. So mercury is a 2 positive, 2 negative for the sulfur, again 1-to-1 ratio. Now to balance this, the only thing you need to do is put a 2 here. And now what about this part right here? What about this? Which one is aqueous and which one is solid? And so this is where we need to look at our formula chart to determine if something is aqueous. So let's go ahead and take a look at this here. This is potassium chloride. It has potassium. So when we look out at our formula chart, what we want to do is we want to find potassium or chloride. We just need to find one of the ions. Now notice here's potassium, right? And chloride, and they're actually in the same section up here. They're in the top half there. And notice that these ions here, these are compounds that contain the following ions are generally soluble. And what that means is it means that they are aqueous. If something is soluble, that means that it will be aqueous when it's put in water. And so this particular compound here is aqueous. That means it will dissolve in water. Now we need to look for one of these, so we need to look for either mercury or sulfide. And if we take a look here, notice how here is the sulfide. This is insoluble. It's insoluble. Now there are these exceptions here, and you need to ask yourself, this is what we're dealing with right here. We're dealing with mercury sulfide, and sulfide is insoluble, which means that it is a solid. Again, soluble means aqueous. And so if it has a sulfide, it's going to be a solid unless it's with one of those ions, which it's not with one of those, so it is a solid. So again, this is a solid. The exception is when it's with one of these. It's not with one of those, so it's a solid. Now, these problems here are asking us to identify the net ionic equation. So what is the net ionic equation? And we're also going to identify the spectator ion. So this is actually really easy. Once you see how this works, it's really easy. The way you identify the net ionic equation is you look at the solid. And whatever is the solid, that's going to be what tells you what is going to be the net ionic equation. And so you take your solid, and all you do is you take the ions of the solid, add them together, to make the solid. And I just cleaned it up right there. So notice how over here, mercury, you can see mercury is aqueous over here. You can also see that sulfur is aqueous over here. And then mercury and sulfur become the solid, and that is the net ionic equation. This here is the net ionic equation. Now we got the net ionic equation from the solid. This here is going to contain the spectator ions. So potassium and chloride are the spectator ions, because notice how chloride is aqueous here and it's still aqueous here. And then potassium is aqueous here and then aqueous here as well. So they start off as aqueous and they end as aqueous. So these contain the spectator ions. Let's go ahead and move on to the next one here. All right, so let's go ahead and go on to this next problem here. Sodium, if you take a look, here's sodium, 1 positive charge. Now carbonate, notice how it ends in 8. That is a polyatomic ion. So you need to look at your polyatomic ion sheet. Carbonate is right here. Carbonate is CO3 2 negative. Calcium, 2 positive, chloride 1 negative. And so you get those from the periodic table. Now sodium is a 1 positive, so this is going to end up being a 2 to 1 ratio. It's going to be Na2. And then carbonate is CO3. Again, got to include that 3 there because because carbonate is CO3. That 3 is a part of carbonate. Calcium is a 2 positive, chloride is a 1 negative, so you need 2 of those. Again, this is a double replacement reaction, so you just make the metals trade places. So now the calcium is with the carbonate. Calcium is a 2 positive, carbonate is a 2 negative. That's a 1-to-1 ratio. And then we end up with sodium chloride, and sodium is a 1 positive, chloride is a 1 negative, again a 1-to-1 ratio. So what we need to do is we need to look at our solubility rules to determine if this is a aqueous or solid compound, and then the same thing with this. So let's go ahead and take a look. So if you take a look here, here's carbonate. And notice how carbonate is insoluble, which means that it is a solid unless it's with one of those. Now the carbonate happens to be with calcium, which is not an exception, so that means it's solid. So this is our solid. Then if you look, here's sodium is soluble, which means aqueous. So if it's soluble, that means it's aqueous. There's no exception, so it's just aqueous. And there it is. So let's go ahead and write our net ionic equation. So again, the net ionic equation is whatever is the solid. Whatever is the solid is going to be what tells you the net ionic equation. So it's the ions of the solid, the aqueous ions of the solid, that's a 2 negative, that's a 2 positive, added together to make the solid. That's your net ionic equation. It's really easy actually. So once you figure out what is the solid, you can then just look at, you can then just make it the ions of the solid added together to make the solid. Now, again, whatever is the aqueous product contains the spectator ion. So this is the aqueous product, this is the spectator ions. Now, what I'm going to do is I'm going to show you a trick that you can do when doing these problems. You don't actually need to write out the balanced chemical equation. And so what you can do is you can recognize that this is the compound that one of the reactants, and then this is another reactant, all right? So we have potassium sulfate, we have barium nitrate. And what ends up happening is because these are reactants, they're added together and the metals trade places, right? So the barium and the potassium trades places to make a product. And so we're going to end up with barium sulfate, and we're going to end up with potassium nitrate, and those are going to be your products. So what you can do is, because you know barium and sulfate are together, you can look on your solubility rules and you can try to find barium or sulfate. Now if you take a look here, here's sulfate. This is sulfate. Sulfate is typically soluble, so this is usually an aqueous ion. So it's typically soluble, except when it's with one of these, it's going to be insoluble. And if you take a look, barium is one of the exceptions. So sulfate typically is an aqueous ion when it's in a compound, but because it's with barium, that means it's actually going to be insoluble. And so our barium sulfate, barium is a 2 positive, sulfate's a 2 negative, so it's a 1-to-1 ratio. This is actually going to be our solid. The barium and the sulfate coming together make a solid because, again, sulfate is typically aqueous except when it's with barium. And so because we've already identified our solid, we can then just write the ions, the aqueous ions, They start off as aqueous, added together to make the solid. Now, this is your net ionic equation. Notice how it's the sulfate and the barium that made the net ionic equation, and the ions that are left over, the potassium and the nitrate, are going to be your spectator ions. So the ones that aren't part of the net ionic equation are your spectator ions, and the potassium and the nitrate are not part of that. So they start off as aqueous and they end as aqueous. And you can even see that potassium and nitrate are both ions that are soluble, and they don't have any exception. Now what I will say is, if you are not able to do it this way, the way that I did number 3, if you need to do it the way that I did number 1 and number 2, then totally do it that way. And I'm going to do number 4 the way that I showed you above. So, because I know that it's hard to see that sometimes. But anyways, potassium, this is a 1 positive, nitrate is a 1 negative, magnesium is a 2 positive, sulfate is a 2 negative. I'll say that this and this, these are polyatomic ions. You got to look at your polyatomic ion sheet. The way that you know that is they end in 8. They end in 8 or ite. You have to look at your polyatomic ion sheet, and that's where you get the charges. So we have potassium nitrate. Again, it's a 1-to-1 ratio. Nitrate is NO3. You have to include the 3. Plus magnesium sulfate. So we have magnesium sulfate. And again, 2 positive, 2 negative means it's a 1-to-1 ratio. And these will go through a double replacement where the metals trade places, and you end up with magnesium nitrate. Magnesium is a 2 positive, nitrate's a 1 negative, so this ends up being a 1-to-2 ratio. Plus, we end up with potassium sulfate. Again, this is a 1 positive, this is a 2 negative, so it is a 2-to-1 ratio. Now what we need to do is determine what is aqueous and what is not aqueous. And if you take a look, the magnesium nitrate, well here's nitrate. Nitrate is soluble, which means it's aqueous, which means it can dissolve in water. There is no exception, so that's going to be an aqueous solution. And then we have potassium sulfate. Notice how potassium here is soluble as well with no exceptions. And if you take a look, both of these products happen to be aqueous. And because they're both aqueous, because there is no solid being produced, that means this is not a precipitation reaction. There is no net ionic equation because both products are aqueous. I know that this was a long video. I realize that there's a lot going on here. This does get easier with practice, and there are independent practice problems on this next page here. This is probably one of the more important concepts of this unit, so definitely make sure that you get this particular concept down, and if you do, you'll be in good shape. Definitely come with questions. You guys have a great day. Take care.